Welcome to lesson 2 of unit 5. So we're going to run through this one relatively quickly. So there's a couple key theorems that are listed in here. So the remainder theorem and the factor theorem and the factor property, all of these things are kind of related together. So as we're working through these examples, just kind of be conscious of that. It's not a ton of examples, as you can see. It basically just breaks down into 4 key ones plus our review at the beginning. So we should be able to zip through this pretty quick, and there is a homework sheet that's tied to this lesson for practice. So if you have any questions, you can ask as usual, and making sure that we're staying on track time-wise. So before we start, it's a good idea to remember how to factor trinomials. So just kind of reviewing that if we have this example, this is a complex trinomial, and so we can look at it one of 2 ways. You can do it guess and check, where we look at factors that try and add up to 7. If you do this, it might look like something like this: 6 and 2x, or 3 and 2, and then maybe 3 and 1. Looking at factors of my first term, factors of my last term, and going across, that would give me negative 2x, positive 9x, which would give me 7x. So I know that this is right. These are my 2 factors. You might have learned it a different way. You're more than welcome to use whatever method you learned. This is just kind of a quick and simple crisscross method that I learned like way back in the day when I was in school. Guess and check sometimes is slow, but if you kind of like logic it out, knowing that like 7 was my target, that's what let me decide where to put things from there. Now those would be my factors. Remembering that we also always want to look for greatest common factors when possible. So the fact that I have x terms in all 3 pieces here lets me factor out an x. And then from there, I will look to see if I can factor it more. So we gain 2x and 1x, how that breaks down. I'm looking at 7 and 2 here. I'm going to put them like that because I need these to multiply to 4x and negative 7x to give me that negative 3x that I want in the middle. So again, these would be my 2 factors. So I'd write, not dropping that x that's out in front, 2x minus 7, and x plus 2. And that would be my final answer for this one. Finally, being able to recognize a difference of squares. So both terms, first of all, it's 2 terms instead of 3, so it's not actually a trinomial. Both of them are perfect squares, which means I'm looking at even exponents on my variables. And so when I go to factor it, I take the square root of my first term plus the square root of my second term. And I'm going to multiply it by the square root of my first term minus the square root of my second term. And that's your difference of squares. Also from our previous lesson, we learned how to divide this out. Again, if I'm using synthetic division, and that's going to be my personal default because I just like that it's a little bit less space that it takes up. 5, negative 2, I make sure that I'm not missing a term. I go x cubed, x squared, x to the 1, x to the 0, so I'm good to go on that front. Write my coefficients. That's where my remainder is going to be. Bring this down. 10, add these, 8. 16, 24, 48, and 47. So my final solution would be 5x squared, always reducing my degree by 1, plus 8x plus 24 plus 47 over x minus 2. That's my remainder. Now, another way we can approach this is by looking at the divisor, and just like when we switch out the signs for synthetic division, And again, just kind of noticing that our sign does not match our sign here. Okay. We can also evaluate our polynomial for when x equals 2. So again, that change of sign from what we're dividing by. Okay, but we're going to plug into our same polynomial and see what happens. And if we do this, so we say p of 2 equals 5 times 2 cubed minus 2 squared plus 8 times 2 minus 1. So that's 8 times 5 is 40 minus 8 plus 16 minus 1 becomes plus 8 minus 1. So that gives me 47. What do you notice from here versus from here? Well, the remainder from my synthetic division is the same as my solution when I evaluate with that same number. So, synthetic division essentially does the same job, it just also gives us our polynomial. So this is called the remainder theorem. And the remainder theorem explicitly states that when a polynomial is divided by some binomial, where a is an integer, some whole number, the remainder is going to be determined by just plugging in that integer for x. So we see this in this example. You could try it on your own. You can note that a, always change your sign. So we're going to change it to positive 3 here. So if this is my polynomial, then I'm going to be saying p of a, or p of 3, is going to be 2 times 3 to the 4 minus 5 times 3 to the 3 plus 5 times 3, not squared. Term, make sure you don't miss any piece, especially for this one. There's a lot of 5s. And from here, you are definitely welcome to use a calculator. I don't remember off the top of my head. I actually do remember that off the top of my head what that is. So this is going to be 162 minus 27 times 5. I'm not sure what that is off the top of my head. I'll have to think about that. Minus, so it's squared. So minus 9 times 5 is 45, plus 15, plus 3. 5 times 27 is 135. Okay, so you can do it mentally. You could also just bust out your calculator. And you could even punch this whole thing in, or if you want to simplify and then evaluate, this would simplify to be 30, 27. This would simplify to be plus 18, so that's 30, 45, so this ends up being 0. Just something to kind of remember is that if your remainder is 0, that means that this binomial goes into this polynomial evenly. Okay, so anytime you come across, oh, don't use that exclamation mark. Thinking back to our previous unit, that would be confusing. Okay, so that's the key idea. That if your remainder is 0, then it goes in evenly. We can test it out here. A would be negative 2, again, remembering opposite signs always. Okay, so then I'm going to plug it in, p of negative 2. It's going to be 2 times negative 2 cubed, not cubed, to the 4. And again, watch out for those transcription errors. Okay, so 2 to the 5 is going to be positive 32. Negative 8, positive 40, negative 20, 10, plus 3. Plus 10, so 42 plus 3 is 45. So again, we do have a remainder, like our previous example, not a, but at the beginning of the lesson, and so it doesn't divide evenly, and so we would have a whole statement with that fraction at the end if we were actually trying to divide this out. And so it means it's not a factor. So the factor theorem states exactly that if you get a remainder of 0, that binomial is a factor. So we would say that x minus 3 is a factor of px. And that's referring to the previous example. And again, if you're struggling with that word factor, remember going back to the definition that you used way back in middle school that we talked about, and I'm just going to write this off to the side, that we would say like 2 and 5 are factors of 10. That means that they would multiply to give us 10. So 2 would be a factor of 10, and so would 5, so we can list them separately. Same thing here. We're not saying what x minus 3 multiplies by to give us that original polynomial, but we're saying that we know that it does divide evenly, and there would be something else it needs to multiply by. So the remainder theorem is definitely a quick way of checking that if something is or isn't a factor. Synthetic division also works, so I'll do a couple of both, just so you can see. If you want to pause the video and try on your own though, now is a good opportunity to pause, and I'll work through the first 2 examples. So I'll work through A and B, one with using the remainder and factor theorems, one using synthetic division and the factor theorem, and finally going through these C and D. I definitely want you trying on your own, but if you need to follow along for A and B to start, that's totally cool with me. So using the remainder theorem and factor theorem, I'm going to do A. So that means that A equals -1. Again, always remembering to change that sign. So if I'm going to substitute -1 in for x, I'm not going to write x, I'm going to write -1. Again, plugging it in everywhere that I see an x, keeping absolutely everything else the same. -1 minus 6 minus 5 plus 12, and that equals 0. So this is a factor. But not 0 is a factor. This is a factor. I might change my color so that I make that final answer obvious. Okay, I could also do this by synthetic division. Still changing the sign of this. I'd go +3, 1 minus 6, plus 5, plus 12, carry down the 1, multiply is 3, it's -3, -9, -4, -12, 0. And so again, I see my remainder is 0, and so this is a factor. So that's kind of convenient. There's more than one factor. And that's quite possible. If you have a cubic, you should have 3 factors. Now, not all of them might be very nice. Some of them might be like decimal values. This one works out quite nicely that it is actually all integers though. So pause the video now if you haven't already. Give these next two a shot, because I'm not going to work through the examples. I'm just going to have my work available to you once I'm done solving them. In these last two examples, because the question is just asking which binomials are factors, and knowing that in order for it to be a factor, when I plug it in, it needs to equal 0. Strictly recognizing that all of this is not going to equal 0 is all I actually need to see in order to decide that this is not a factor. Similarly, by completing this calculation, I see that it is equal to 0, so it is a factor. But I don't actually need to finish my arithmetic because my arithmetic isn't what's important here. Identifying that it does or doesn't equal to 0 is the key idea behind that factor theorem. So as long as you can see that and you can state that it doesn't equal 0, the actual value doesn't matter unless you're explicitly asked what is the remainder, or state this polynomial in factor form, in which case you would need to account for remainders. So finally, the factor property, which is our third property and our last piece of this lesson, states that if our binomial, when a is an integer, is a factor of a polynomial, then a is a factor of the constant term in the polynomial. So basically what that's saying is that for whatever binomial you're factoring out, the number at the end of that binomial needs to be a factor of the constant term at the end of your polynomial. Okay, so a needs to be a factor of 6. So that means that all my possible options include plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, based on the fact that my constant is 6 at the end of this. So from there, I can try and figure this out. So I'm going to use synthetic division just because that gives me all the pieces to work with, not just telling me if it is or isn't a factor. So that's just my personal preference. I'm going to just start with 1 because it's very, very easy. I fill it in, I check that my exponents are descending by 1 each time, 3, 2, 1, 0, perfect. So 2 minus 9, 7, and 6. Let's see how this goes. So carry the 2 down. 2 times 1 is 2, that's negative 7. 0, 6. Not a factor because the remainder isn't 0. So even though I had a 0 showing up in my actual polynomial, not a factor because not 0. Okay, so I could try negative 1 though, see if that works. Negative 11, positive 11, 18, negative 18. No, I know that's not going to equal 0, so I can keep going. So try positive 2, same thing. Always carry down that first one. Okay, so now that I've found one factor, now I might be able to simplify this further. So I'm going to pause for a second and write, okay, 2x cubed minus 9x squared plus 7x plus 6 equals x minus 2, because remembering I always change my sign for synthetic division. And then my remaining polynomial is 2x squared, reducing my degree by 1, minus 5x minus 3. And I look at this and I'm like, I think I can factor that without having to do synthetic division or long division or anything like that. I think I've got the skills for factoring a trinomial. So once I've got that x minus 2 up front, I don't want to drop it because it's important. It is a factor. It's part of the multiplying to create this full polynomial. But I look here and I'm like, okay, well, how does this break down? Well, I can take 2x and x. 2 plus 3 equals 5. So if I go that I need opposite signs, so I'm going to go with negative 3 down here because also 6 minus 1 equals 5. And these are going to be my two factors. So I look and I say, okay, well, that ends up being 2x plus 1 and x minus 3. And so that's my fully factored form. And I'm done. So by being able to factor this trinomial through the means that we learned in grades 10 and 11, it saves me a little bit of work in terms of continued synthetic division. So I can stop here once I've gotten it down to a quadratic or a degree of 2. Our last example, fully factor this guy. So again, I look at this last term and I'm like, okay, those are my factors to work with, my a values to work with, potentially. So my a's can be plus or minus 1 and plus or minus 2. So this is a nice one because it's very, very restricted. So there's not a whole lot to guess and check. So again, I'm going to start with 1 because it's simple. I'm going to do synthetic division instead of using my remainder theorem because that's just a personal preference. I double check 3, 2, 1, 0, so I don't need to fill in any extra missing spaces with zeros for different terms. Carry my first down and go from here. That's not going to equal 0, so I can stop. Oops, again, synthetic division, I don't need to include my x's. Carry this down. I always draw the arrow there to remind myself that I'm not writing any values in here. So, negative 3, negative 7, 7, 2, 2, 0. Perfect. Factor. So again, I pause at this point and I'm like, okay, well that means that 3x cubed minus 4x squared minus 5x plus 2 equals x plus 1, because again, synthetic division means I change the sign, and I'm left with 3x squared, because I decrease my degree by 1, minus 7x plus 2. And I look at this and I'm like, I think I can factor that again, just like my previous example, and so that's exactly what I'm going to do. I'm going to use my crisscross method of 3x and x, 2 and 1. They're both going to be negative so that they multiply to give me a positive, but then add to give me a negative here. So it's going to be 3x minus 1 and x minus 2. And that'll be my final fully factored form, because I can't factor that anymore. Okay. So again, there is a practice worksheet here. It's got synthetic division, use synthetic substitution, aka the remainder theorem. So you might see this language, not so much on the provincial exam, they'll stick to remainder theorem, but synthetic substitution is the remainder theorem. And then for these last question, they're asking you to fully factor, just like we did there. Solutions are all listed. You know what, you're only going to be able to do a couple of these. So I'm going to get another worksheet to go with them, because all these things that have I's in them, you're not going to be able to do. So don't worry about 9, 10, 13, or 14. That's crummy. I'll find another worksheet for you to do. Okay, and the reason you're getting square roots showing up is because you can use the quadratic theorem. So 12 is the good one because it's got some nice clean ones. I'll find some better worksheets for you and add them in here. But again, if you have questions, always ask. And if you get stuck, always ask. Ask me, ask a teacher at your school, ask a classmate, peer, whatever you need to do to make sure that you are understanding this.